Okay, very good morning to all of you. And today we'll be going with our next topic in our syllabi, and that's we would like to discuss the degenerate time-independent perturbation theory. In our previous classes, what we have done is we have gone through non-degenerate perturbation formalism, and we tried to solve some of the numerical problems falling in the framework of non-degenerate perturbation theory. Now, the point is, let me introduce you first with degenerate model, and then we will go with the mathematical treatment of degenerate perturbation theory. Now, to start with, I'll be giving this introduction to this degenerate time-independent perturbation theory, and you can see that we will be introducing you with the concept in this presentation. Now, again, I'll go back to the point of perturbation. What perturbation is, it's basically a very simple disturbance that you are exerting on your system of whose Hamiltonian is already known, and you have calculated all the eigenvectors and eigenvalues linked with that Hamiltonian problem. So what we have perturbation, and it's a mathematical technique that's used to approximate the solution of a problem, of whose solution is already known. So this way you are able to solve the complex problem using the simple idea of perturbation. So in time-independent perturbation theory, what we assume that the Hamiltonian of the system is slightly modified. So the disturbance is not huge, the disturbance is very small, and then what we do, we analyze how this small change affects the system energies and states. Now the point is, what is degeneracy? Okay, degeneracy means you have more than one quantum state in which the energy of the particle is same. This is what we call as degeneracy. And if you take an example of hydrogen atom, 2s and 2p orbitals, they are degenerate orbitals, okay? Their energies are same. So degeneracy refers to a situation where two or more quantum states, they share the same energy level. But the point is, in absence of external disturbance. Okay? The point is, you have an ideal system and you have degeneracy between different orbitals in an atom. And this degeneracy is there only in absence of external perturbation. So the example is 2s and 2p orbitals of hydrogen atom problem, because hydrogen is it's a spherically symmetric problem, right? So that's why you can see the degeneracy among 2s and 2p orbitals in absence of the external fields that you may apply. Now, why is this degeneracy special? Why is it special? When energy levels are degenerate, the standard approach that we have, you remember when we chose the problem of non-degenerate system and we calculated the first order correction or the second order correction in the eigenvector of your problem, in the denominator, if you remember, you had En minus En. So En, when I say degenerate, En is equal to En. So that means the theory that we were discussing previously, that is incompatible with the problem that we have been discussing. Because in this problem, you have a range of energy levels which are having the same energy. You got my point? So that standard approach fails. The perturbation theory fails. So we certainly must consider the effect of perturbation on the entire subspace degenerate states. So you have to develop a new framework, and you will entirely choose a different framework, a basis vector. In that vector space, you will choose the vectors who will have same energies. Getting my point? Okay. The physical examples about the degeneracy. Degeneracy commonly occurs in atomic and molecular systems. The example is hydrogen, and as I said, hydrogen has spherical symmetry. And you have the example one, electron states in a spherical potential. If your potential is spherically symmetric, energy levels in a quantum harmonic oscillator with isotropic potential. If you choose an isotropic potential for harmonic oscillator, you will have the degenerate energy levels. And the orbitals that you have in an atom like px, py, and pz. If you remember the p orbital, it has three components: px, py, and pz. So they are the three different orientations of p orbital having same energy. Now, how will you know anything about degeneration? You will know about degeneracy only when you will disturb your system. How do we know anything about the nucleus? This is a question for you. Come on. You are saying, come on, nucleus has protons, neutrons, okay? And further, these protons and neutrons, they are made of some more fundamental particles like quarks. How do we get the information? Suppose there is a person, he is hiding something, and you have to investigate what this person knows. What you will do? You will interrogate him. So nucleus is not going to tell us what am I. For that you have to interrogate the nucleus. You can, whatever theories that we have till now about the nucleus, they are because of the exploitation. We are able to exploit the nucleus. When we exploit the nucleus, it tells us. In certain cases, it breaks down. You have alpha particles. You have radioactive nucleuses, right? So, disturbance, external disturbance basically is a technique to know what exactly is going on in your system. So it's like you are interrogating the nucleus when you hit the nucleus with a projectile. Getting my point? So the same thing is here, that if there is a degeneracy, it must be lifted. So this is called a lifting of degeneracy. A perturbation lifts the degeneracy by splitting the energy levels. You apply some disturbance to your system, you find where you find no difference in energy, you find there is difference in energies. So what you do? You introduce the perturbation and the degeneracy is eliminated. It's eliminated from your system. The example is Zeeman effect. You apply the magnetic field, you have the splitting of energy levels. So you will say, why there is the splitting of energy levels? What could be the basic reason for that? The reason could be that all of these energy levels must have the same energy. Once I am introducing the perturbation to the system in the form of magnetic field, what you find? You find the splitting of energy levels. So what's the strategy to solve this problem? So instead of solving for individual states as in case of non-degenerate, we focus on the entire subspace here. And we construct a matrix of perturbation within the degenerate subspace, and then we diagonalize it. Once we diagonalize it, we are able to calculate the discrete values of energy eigenvalues. So, in degenerate system, what we do, we must choose a new basis, then diagonalize it, and the perturbation within the degenerate states, this ensures accurate prediction of the energy shift. Then you introduce the perturbation, and then you see that how discrete energy levels are naturally coming out of your system. So what we choose a degenerate subspace. What is a degenerate subspace? It's a collection of all states. As I said, it's a collection of all the states sharing the same energy. Within this space, what we do, we analyze the perturbation, mixes these states. Once I include the perturbation in my system, it certainly does what we expect from it. And what we do, we diagonalize it. Okay? To repeat the topic, by diagonalizing the perturbation matrix within the degenerate subspace, we find the new energy levels and the correct linear combination of original states that are existing in your system. Physical implications, you know about them. Degenerate perturbation theory explains the phenomenon like Zeeman effect and Stark effect. And this theory is very crucial in condensed matter physics, atomic physics, spectroscopy. It certainly helps us understand electron behavior in the crystals. You remember the crystals having periodicity in them, the periodic potential, and the electron is propagating in that periodic potential. And when we solve the problem of electron moving in a periodic potential, we conclude the band theory of solids, what's called as Cronin-Penny model, right? So there it also plays an important role. It has limitations. What are these? The method assumes the perturbation because the actual systems cannot be this much delicate. The actual systems will have strong, where you apply the strong perturbations to your system, this theory does not give you the accurate predictions. So degenerate perturbation theory is a powerful extension of quantum mechanics. It's essential for understanding systems with symmetry and closely spaced energy levels. So I'm using very closely spaced energy levels. What we generally say, same energies, right? So this is the introduction of degenerate perturbation theory. Now let's move on to discuss the mathematical formalism of degenerate perturbation theory. Okay, so if anybody has any questions, you can ask me. Now the point is, I want to exit from here. Okay, so the point is, we will be discussing degenerate time-independent perturbation theory. So our problem is degenerate. My handwriting is very bad. Time-independent perturbation theory. This is our target. So what we have a perturbed Hamiltonian, right? So if I assume that my perturbed Hamiltonian operator is H prime, or I may call it HP, this is the perturbation that I am introducing into the original Hamiltonian, right? So this H will be the combination of H naught plus HP. Now H naught is completely known to us from energy eigenvalues to energy eigenvectors, right? We know everything about H naught, exactly we know everything about H naught. And we are incorporating a small perturbation to our system. So H here is the summation of the Hamiltonian of the unperturbed system, and you add the small perturbation to this Hamiltonian. So we have to choose a basis vector. We have to choose a subspace, making sure that subspace has degeneracy in it. Clear? Is this clear up to this point? Can I wrap this? Okay. Now, if I choose psi and alpha, this is my energy eigenvector. And you can write this energy eigenvector in terms of the superposition of the unperturbed energy eigenvector. So how can I write this? I can write this as summation of, say, A alpha psi n alpha naught. What this alpha that I have introduced here, this alpha can run from 1 to say f. Now running from 1 to f means that my system has f-fold degeneracy. Okay? I choose my system with f-fold degeneracy. Now what I have the vector space psi and alpha. I write down it as a superposition of vector space of psi and alpha naught. Psi and alpha naught is known to us, and I introduce a coefficient, A alpha with it. Is this clear? Is this clear to you? Okay. Now this is ket. If I want to write down its bra, what will I write? So for the bra, I will have sine and alpha will be equal to sigma. Alpha runs from 1 to f. A alpha star. Am I right?
Yes.
And what about this? It will be bra of sine and alpha naught. Right? These are my two story equations that I choose here. And obviously, I would like to take the inner product of these two vectors. Because, see, why I am doing the inner product? Because I want to know the value of this A alpha. Right? I want to know the value of this A alpha. So in order to calculate that, what I do, I take the inner product between these two vectors. Okay? So when I do that, what should I write? I should write psi and alpha. Psi and alpha is equal to sigma. Now you know it is from 1 to f. I will not write that. So you will have A alpha star, and then you will have psi and alpha naught and psi and alpha naught. So when we start discussing our problem, when we start discussing the theory, we presume that the wave function is, we start with that orthogonality condition, right? We start with that canonical delta. For alpha, for the same eigenstates, the value is equal to 1. So if I do that, what will I get? For this, I will get 1. This is equal to sigma. This is A alpha star. It is mod of A. It's mod of A alpha square, and this is equal to 1. So what does that mean? That means this sigma A alpha, its magnitude is equal to 1. So the A alpha that we introduced here as a coefficient of each eigenstate having same energy, its value is 1. Okay? Now let's move on. Can we move on? Okay. So this thing is known to us, that sigma A alpha whole square is 1. Okay? Now, let's go back to our problem. And what's our problem? Our problem is, this is a perturbed Hamiltonian. And this Hamiltonian is acting on a vector space psi and alpha. And from here, we are expecting the energy eigenvalues, and we have psi and alpha back. Because this Hamiltonian is assumed to be a Hermitian operator. Right? So for H, what can I write for H here? Now this is, so for H I can write H naught plus HP and then sine psi and alpha equals En psi and alpha. Am I right? Is it right? Come on, any questions? Now, I want to write my energy eigenvector in terms of unperturbed energy eigenvectors. I want to solve my problem in the framework of what is known. So for that, for this psi and alpha, what I will use? I will use sigma A alpha, psi and alpha naught, right? So what should I write here? This is H naught plus HP. I will introduce sigma, then you will have A alpha and psi and alpha naught, right? So in the right hand side, you will have En is a number, get it out, so you will have sigma A alpha psi and alpha naught. Come on, is this clear? Okay, so up to this I think things are clear. So we can move from here. Now we will take the ordinary multiplication here. We will put the corresponding energy eigenket to the corresponding operators. So the next step that we will have, what will be that? That will be sigma A alpha. Then you will have, I would like to introduce a bracket here. Then you will have H naught psi and alpha naught. This will be term number 1. And what will be the next term? HP psi and alpha naught. I'll close it. I will close the bracket. Right? And in the right hand side, what you have? Sigma. Yeah. You have A alpha. Then you have En is out. Let me write that out. En psi and alpha naught. Fine? Right? Okay. Now let me introduce another basis in the same unperturbed framework, and let me introduce that as the bra psi and beta naught. Okay? And if this bra psi and beta naught acts on H naught, what will you get? Come on, what you'll get? You will get psi and beta naught E. I will use M here. No, En, sorry. It has to be E and naught. Clear? This is your energy eigenvalue equation in terms of the bra vectors. Is this clear? Okay? And obviously, we understand that the orthonormality will exist. Psi and beta naught, psi and alpha naught will be equal to the chronicle delta. Delta alpha beta. So you can understand that your equation will exist for alpha equal to beta, right? If alpha is equal to beta, the equation is going to exist. Is this clear up to this point? Now, this is my original equation. And what will I do is, I will multiply this equation from left. I will multiply this equation from left by the bra of psi and beta naught. Is this clear? Is this clear? Yes, come on. So move on. So what you will have? Psi and there is a sigma. I should rub it again. So there is a sigma and then there is A alpha, and then there is a bracket, then I have psi and beta naught, then I have H naught, then I have psi and alpha naught. Is this clear? This is the first term. The second term is psi and beta naught. You see your perturbation is falling in the framework of unperturbed eigenstates. So this is HP and psi and alpha naught. Okay, is this clear?
Yes.
Now this is equal to, okay, you have En and then you have sigma. Come on, A alpha. Now you will have psi and beta naught, and you will have psi and alpha naught. Is this clear up to this point? Clear? Okay, fine. Now for this, what can I do? I can get this H naught out because I will use the energy eigenvalue equation, right? So what will be the next step? It will be sigma A alpha. Okay, here you will have E and naught is out. Okay, what will be inside? Psi and beta naught, psi and alpha naught. Clear? Okay, then plus, same thing, psi. Now I would like to make it a little bit simpler. For this, because it's a matrix element, this is to be evaluated, so for this I will write HP alpha beta. Any problem? Well, this HP alpha beta is representative of this matrix, okay? Fine? Okay, the bracket will close, and in the right hand side you're left with En sigma A alpha and psi and alpha and psi and beta, naught and naught. Clear? Fine? Now, you can see that this thing will exist, okay, for alpha equal to beta. So what you will have? You will have the first term as sigma A alpha E and naught. The first term will be sigma A alpha E and naught plus HP alpha beta. Clear?
Yes.
Is equal to sigma A alpha En. What am I choosing? I'm choosing alpha equal to beta. It will exist for alpha equal to beta. Right? So, this is my question. Right? Now, if I assume that my energy is En, this is the total energy of the perturbed system, I can write it as En naught plus En1. Let me take it to the first energy correction, right? So En is En naught plus En1. So what is En1? En1 is En minus En naught. Is this clear? So En1 is En minus En naught. Now you see, here you have En naught. You bring that, you take this on the other side, take everything on the other side. Okay, you can do that. The choice is yours. Now if I bring it back, what you will get? Can I rub this or I'll move on? I would like to rub it here because otherwise, so keep this thing in mind. It is En minus En naught. Okay, so this is sigma A alpha. Okay, bring that here. So this is En naught minus En. Yeah? Then you have plus A alpha HP alpha beta is equal to 0. Right? Okay, fine. Okay, so what can we do? This is En naught minus En. What is it equal to? It is equal to minus En1. Okay? So this is sigma. A alpha is common to both now. So this is En1, that to minus, right? And this is your plus H P alpha beta is equal to what? Is equal to 0. In the beginning of this mathematical treatment that we started with, if you rightly remember what I did, I proved that sigma alpha is not equal to 0. Sigma A alpha is not equal to 0. You know that? You remember that? Sigma A alpha is not equal to 0. You can check that equation that we obtained in the very first of this class. So if this is not equal to 0, then what is equal to 0? The bracketed term is equal to 0. So I can write this now. What you will have? You will have sigma HP alpha beta minus En1 is equal to 0. Right? You remember that this equation is giving you these values for the diagonal of the matrix. Because for alpha not equal to beta, your answer is 0. Right? So this equation will give you the correction. So how can I write this equation now? Come on. So my equation is like this. You have HP11 minus En1. HP22 minus En1. HP33 minus En2, and so on and so forth. And here you will have HP12, HP13, and so on and so forth. In this case, the correction will not add, because for alpha not equal to beta, the value of this En is 0. And the same story will go in this side. HP, this was 1, 1, this is 2, 1, and so on and so forth. So these diagonal elements give you the degeneracy. And what does this result tell us? Yes? HP22 minus? No, it is only the correction in 1. It's En1. It's En1. It's En1 in every case. Okay? Okay, this is 1. This has to be 1. Right? Okay? So the other elements will show no splitting of energy there. Now, what do you conclude from this result? The matrix that you have obtained. What is the conclusion of this class? What does this matrix tell me? The conclusion of this class is that when you apply the perturbation to your system, it lifts the degeneracy of your system, and you have discrete different energy eigenvalues, and that is confirmed by the matrix that is in front of you. Yes. So with this, anybody having any queries, you can ask me. Yes? Okay? No? So you can close it, and we will see for more things coming.